Hello and welcome to Deep Learning and Natural Language Processing Masterclass. I'm Mike West and I'll be your instructor for this course. We are inundated with text from books, papers, blogs, tweets, news, and increasingly text from spoken utterances. Working with text is hard as it requires drawing upon knowledge from diverse domains such as linguistics, machine learning, statistical natural language processing, and these days, deep learning. I've designed this course to teach you a step-by-step how-to bring modern machine learning methods to your natural language processing projects. In the course, you'll use Python, the top language in the applied space for building machine learning models. You'll use Python programming libraries and tutorial topics to give you the skills you need to understand this niche area of machine learning. The course will focus on showing you how to use the best-in-breed Python tools for natural language processing, such as GenSim, NLTK, and scikit-learn. The gold standard in RAPO prototyping deep learning models in the applied space is Keras, and in this course, that'll be the library you use to build your end-to-end models with. The course was designed around major activities, techniques, and natural language processing problems. There are a lot of things you could learn about deep learning and natural language processing, from theory to applications to APIs. The main course goal is to take you straight to getting results with laser-focused tutorials. This is an applied course, and that means it's hands-on. The lessons throughout the course and the tutorials will give you the tools you need to both rapidly understand and apply each technique to your own natural language processing prediction problems. Thank you for your interest in Deep Learning and Natural Language Processing Masterclass. Let's get started. Hello and welcome back. In this lesson, let's talk about the course content. The course is divided into 8 sections. On Udemy, a section is like a chapter in a book. So section 1 is going to be about foundations. It's going to introduce you to natural language processing, deep learning, as well as tutorials on how to get started with Keras. Keras has become the gold standard for building deep learning models in the applied space. Section 2 is about data preparation. You'll learn how to clean, prepare, and encode text for modeling with neural networks. Section 3 is about a model called a bag of words model. You'll learn how to create a bag of words model, a staple representation for machine learning and a good starting point for neural networks for sentiment analysis. In Section 4, you'll learn about word embeddings. In this section, you'll learn about powerful word representations and word embeddings, how to develop them as standalone models, and how to learn them as part of neural network models. Section 5 is all about text classification. In this section, you'll learn how to leverage word embeddings and convolutional neural networks to learn spatial invariant models of text for sentiment analysis, a successor to the bag of words model. Section 6 is all about language modeling. You'll learn how to develop character-based and word-based language models, a technique that is required as part of modern text-generating models. You'll learn how to combine pre-trained object recognition models with a language model to automatically caption images. In Section 8, you'll learn about machine translation. You'll learn how to combine 2 language models to automatically translate text from one language to another. By the end of this course, you'll have a solid foundation for understanding and building natural language processing models using deep learning. Hello everyone and welcome back. In this lesson, let's decide if this course is right for you. The first thing I'd like to say is this is not an entry-level course. If you need an entry-level course on Python for machine learning engineers, then check out my course, the Complete Python course for machine learning engineers. This will provide you with all the skills you need in order to take this course, Deep Learning with Natural Language Processing. Because deep learning is kind of a niche within the machine learning space, and NLP is also kind of a niche within the machine learning space. So we have these 2 niches which make it a little more difficult. So who is the course for? Number 1 is for programmers. If you're a programmer, specifically a Python programmer, or really any programmer, and you're thinking about or you've decided to make the switch to a machine learning engineer, then this course is for you. This is going to give you tons of insight into building natural language processing models using deep learning. Secondly, if you're a data professional and you're in the same boat as the programmer, you are thinking about making a move to a machine learning engineer, and you're interested in learning natural language processing specific to deep learning, this course is for you. Thirdly, maybe you're new to the space altogether. However, you're interested in natural language processing, and you're interested in deep learning, and you've had some courses on Python, and maybe a course on deep learning, then this course is for you. Now, if you're in one of these 3 categories, then this course is for you. You are my target audience. If not, go ahead and take a Python course, go ahead and take some basic machine learning courses, and then come back and take this one. In this course, we're going to learn about natural language processing using deep learning models. Natural language processing, or NLP for short, can be broadly defined as the automatic manipulation of natural language, like speech and text, by software. The study of natural language processing has been around for more than 50 years and grew out of the field of linguistics with the rise of computers. The ultimate objective of NLP is to read, decipher, understand, and make sense of human languages in a manner that is valuable. Natural language refers to the way we humans communicate with each other, namely through speech and text. We are surrounded by text. Every day we see signs, menus, emails, SMS messages, web pages. The list really is endless. Now think about speech. We speak to each other, as a species, more than we write. It may be even easier to learn to speak versus learning to write. Voice and text are how we communicate with each other. Given the importance of this type of data, you must have methods to understand and reason about the natural language, just like we do with other types of data. Working with natural language data is not solved. It's been studied for half a century, and it's really hard. Natural language is primarily hard because it's messy. There are very few rules. And yet you and I can easily understand each other most of the time. Human language is highly ambiguous. It's also ever-changing and evolving. People are great at producing language and understanding the language, and are capable of expressing, perceiving, and interpreting very elaborate and nuanced meanings. At the same time, while we humans are great users of language, we are extremely poor at formally understanding and describing the rules that govern the language. Human brains interpret real-world situations in ways that computers can't. Neural networks were first developed in the 1950s to address this issue. An artificial neural network is an attempt to simulate the network of neurons that make up a human brain so the computer will be able to learn things and make decisions in a human-like manner. ANNs, or artificial neural networks, are created by programming regular computers to behave as though they are interconnected brain cells. Artificial neural networks use different layers of mathematical processing to make sense of the information it's fed. Often, an artificial neural network has anywhere from dozens to millions of artificial neurons arranged in a series of layers. The input layer receives various forms of information from the outside world. This is the data that the network aims to process or learn about. From the input unit, the data goes through one or more hidden units, or hidden layers. The hidden layer's job is to transform the input into something the output can use. The hidden layer is the computational layer. The input and output are not computational layers. They are simply layer to accept the data and output that data. In our diagram, the first layer shows the input layer. It's accepting data. It's accepting or being passed two pieces of data. The second layer is the hidden layer. These layers are the computational layers. The last layer is the output layer. It outputs the calculation done by the neural network. And our diagram represents the most basic artificial neural network that can exist. It is an artificial neural network with one hidden layer. All artificial neural networks are composed of artificial neurons. They are not only named after their biological counterparts, but they are also modeled after the behavior of the neurons in our brain. Like a biological neuron, an artificial neuron has several input channels, a processing stage, and an output that can fan into multiple artificial neurons. Let's zoom into this process a little further. How does a neuron process its input? There are three core processing steps. In the first step, a signal comes in and it gets multiplied by a weight value that's assigned to the input. If a neuron has three inputs, then it has three weights that can be adjusted individually. During the learning phase, the neural network can adjust the weights based on the error of the last test results. Step 2. In the second step, the modified input signals are summed up into a single value. In this step, an offset called a bias is added to the sum. The neural network also adjusts the bias during the learning phase. At the beginning, all neurons have random weights and random biases. After each learning iteration, these weights and biases are gradually shifted so that the next result is a bit closer to the desired output. This way, the neural network gradually moves towards a state where the desired patterns are learned. In the third and final step, the results of the neuron are calculated and then turned into an output signal. This is done by feeding the result into an activation function. In the last lesson, you learned about the core parts of an artificial neural network. Well, the next question you might have is, okay, now I know what a neural network is. What makes a neural network a deep learning model? Well, the truth is, it's still up for discussion. Here's what we do know. We know that a deep learning model is contingent on the number of hidden layers. We call that a hidden layer as a computational layer. We know that a deep learning model is an artificial neural network with X number of hidden layers. The question then becomes, well, what is X? The answer is, we really don't know. While we don't know the exact tipping point that makes a neural network a deep learning model, we know it's contingent on the number of layers, and it's probably more than 2 or 3. Hello and welcome back. In this lesson, let's talk about and learn about Keras. Keras is one of the leading high-level neural network APIs. It's written in Python and supports multiple back-end neural network computational engines. Let's craft a list of items that will give us some more insight into Keras. Firstly, it was created by a Google intern named Francois Cholet. I know I'm butchering his name. I'm sorry, Mr. Cholet. Secondly, it's a high-level library. High-level means it's easy to use and easy to understand. Keras is a library. Take note, I didn't say it was a language. It's not a language or even a framework. It's a library. It cannot live on its own. Keras uses one of these 3 backends: TensorFlow, CNTK, or Theano. The word backend means that all the heavy lifting, the computational tasks, are taken care of at the framework level. TensorFlow, CNTK, and Theano are often referred to as the frameworks. Think of frameworks as the engine. Keras was designed for building deep learning models. It's not used for building traditional learning problems. Lastly, TensorFlow, which was written by Google, is probably the most widely known deep learning framework. In its latest release, called TensorFlow 2.0, Keras has been tightly integrated into the framework. And that wise decision by Google has helped Keras become even more popular than it was before. Hello and welcome back. In this lecture, let's take a look at the Keras lifecycle. The first step in this lifecycle is to define your neural network. Neural networks are defined in Keras as a sequence of layers. The container for these layers is called the sequential class. The first step is to create an instance of this sequential class. Then you create your layers and then you add them in order they should be connected. For example, let's take a look at this example on screen. The first layer in the network must define the number of inputs to expect. The way that this is specified can differ depending on the type of network. But for a multi-layer perceptron model, this is specified by the input dim attribute. For example, a small multi-layer perceptron model with 2 inputs in the visible layer, 5 neurons in the hidden layer, and 1 neuron in the output layer can be defined as seen on screen. Think of a sequential model as a pipeline, with the raw data fed at the bottom and predictions that come out at the top. The choice of the activation function is most important for the output layer, as it will define the format the predictions will take. For example, let's take a look at a few modeling types and the structure and standard deviation function that you can use in the output layer. For regression, there's linear activation functions. For binary classification problems, there's logistic activation functions. And for multi-class classification, there are softmax activation functions. Once you've defined the network, you must compile it. Compilation is an efficiency step. It transforms the simple sequence of layers that you defined into a highly efficient series of matrix transformations in a format intended to be executed on a GPU or CPU, depending on how Keras is configured. Think of compilation as a pre-compute step for your network. It's always required after defining the model. Compilation requires several parameters to be specified, specifically tailored to your training network. Specifically, the optimization algorithm to use to train the network and the loss function used to evaluate the network that is minimized by the optimization algorithm. For example, on screen, we've got a case of compiling a defined model and specifying an SGD, or stochastic gradient descent optimization, and the mean squared error, intended for regression-type problems. Alternatively, the optimizer can be created and configured before provided as an argument to the compilation step. The type of predictive modeling problem imposes constraints on the type of loss function that can be used. Let's go ahead and cover a few standard loss functions for different predicting modeling types. So for regression problems, we have mean squared error. For binary classification problems, we have logarithmic loss. It's also known as cross entropy or binary cross entropy. And for multi-class classification, we have multi-class logarithmic loss or categorical cross entropy. Lastly, you can specify metrics to collect while fitting your model in addition to the loss function. As a general rule, the most useful additional metric to collect is accuracy for classification problems. The metrics to collect are specified by name in an array. Once a network is compiled, it can be fit, which means adapting the weights on the training dataset. Fitting the network requires that the training data be specified, both a matrix of input patterns X and an array of matching output patterns Y. The network is trained using backpropagation. and optimized according to the optimization algorithm and the loss function specified when you compiled the model. The backpropagation algorithm requires that the network be trained for a specified number of epochs or exposures to the training dataset. Each epoch can be partitioned into groups of input and output pattern pairs called batches. This defines the number of patterns that the network is exposed to before the weights are updated within each epoch. It's also an efficiency optimization, ensuring that not too many input patterns are loaded into memory at one time. A minimal example of fitting one network is on screen. Once fit, a history object is returned that provides a summary of the performance of the model during training. This includes both the loss and the additional metrics specified when compiling the model, recorded for each epoch. Training can take a long time, from seconds to hours to days depending on the size of the network and the size of the training data. By default, a progress bar is displayed on the command line for each epoch. This may create too much noise or may cause problems for your environment. For example, if you're using an interactive notebook or an IDE, you can reduce the amount of information displayed to just the loss of each epoch by setting the verbose argument to 2. You can completely turn off the output by setting verbose to 0, as shown in our example on screen. Once a network is trained, it can be evaluated. The network can be evaluated on the training data, but this will not provide a useful indication of the performance of the network as a predictive model, as it has seen all this data before. You can evaluate the performance of a network on a separate data set, unseen during testing. This will provide an estimate of the performance of the network at making predictions on unseen data in the future. The model evaluates the loss across all test patterns, as well as any other metrics specified when the model was compiled, like classification accuracy. A list of evaluation metrics is returned. For example, a model compiled with an accuracy metric, you could evaluate it on a new dataset as shown on screen. Once you're satisfied with the performance of the fit model, you can use it to make predictions on the new data. The predictions will be returned in the format provided by the output layer of the network. In the case of regression problems, these predictions may be in the format of a problem directly, provided by a linear activation function. For a binary classification problem, the predictions may be an array of probabilities for the first class that can be converted to a 1 or a 0 by rounding. For multi-class classification problems, the results may be in the form of an array of probabilities, assuming a one-hot encoded output variable that may be needed to be converted to a single class output prediction using the argmax numpy function. Alternatively, for classification problems, you can use the predict classes function that will automatically convert uncrisp predictions to crisp integer class values. This is the complete Keras model lifecycle. Hello and welcome back. All right, now I do realize that last lesson was a little dry, but I think it's important to understand the first part of it, especially the anatomy of a model. Now let's put all that knowledge to work and build it into model in Keras. So the first thing we're going to do is import sequential, and we're going to import dense. Recall that sequential is the definition. It's used to define the neural network. We're also importing dense from layers, and we're going to import numpy. In the second cell, we're going to set our seed for reproducibility. And in the third cell, we're going to use pandas. We're going to import read CSV and bring in a file to use. I will include the file, and this notebook actually, in the lesson. So we're going to create an array for our data frame. In the next cell, we're going to set X and Y. X is going to be the data that we're going to use to train and test on. Actually, I don't think I have anything here to separate the data. Nope. So to train on, to train and test on. And Y is going to be the target variable. And in the next cell, we're going to take a look at the data frame using the head function. After we do that, we're going to move on to the next section. And this is Keras. Model equals sequential. Tells Python everything that comes next is going to be part of the neural network. Model add. Adds each layer. So how many layers do we have here? Right, 3. So in the first line, dense. The 12 represents the number of neurons in this specific layer. Next, we have input dim. That's input dimensions. Those are the number of individual cells that we're going to train on in our array. The initialization function is uniform, and the activation function is ReLU. That's all in the first layer. The second layer, we're going to add 8 neurons. We're going to use uniform as the initialization function, and we're going to use ReLU as the activation function. In the third layer, we've got 1. Why 1? Well, that's the output layer. This is a binary classification problem. It's going to be a 1 and a 0. Right? So that's why there's only 1 neuron in this last layer. The initialization function is also going to be uniform. The activation function is going to be sigmoid. On to the next cell is compilation. Model.compile. We're going to use binary cross entropy. We're going to use atom as the optimizer. And for metrics, since this is a classification problem, we're going to use accuracy. In the next cell, we're going to call the fit function on our model. We've got X and Y. We've got the number of epochs is 200, and the batch size is 30. And lastly, we're going to score a model. And our score on this particular data set is a 72%.